Hello everyone, and welcome back to my channel. Today, we're diving into an exciting Qt for MCUs project, the DrinksBar application, running on the STM32F769I discovery board. Let's start by previewing the outcome of this tutorial. You'll see a sleek, touchscreen interface for ordering drinks, complete with vibrant images and a real-time clock. In my last tutorial, we built a DrinksBar application for the desktop using Qt. This project adapts the same QML-based GUI for an embedded system. If you're new to Qt or want a refresher, check out my previous video linked in the description, then come back to this one. To save the board's limited memory, we dynamically load these images from an SD card in real time and clear them from memory after display. This approach optimizes memory usage, leaving more resources for other tasks. Drink information, like names and image paths, is stored in a JSON file. That JSON file also loaded from the SD card. By parsing this file with the drinks model class, we populate the UI with drink options without storing data in the board's memory. I added the Japanese translation function to demonstrate how easily Qt for MCUs supports multilingual applications. To show you how to work with the MCU's RTC clock, I've implemented the real-time clock and its setDateTime function, which I'll explain in detail in this tutorial. This makes the app scalable for complex UIs with images or even videos. Let's dive into the code to see how it all works. In my last video, we used a Figma template as a reference for the DrinksBar UI. If you want to check it out, I'll include the link in the description. The STM32F769I discovery board is fully supported by Qt for MCUs. It comes with a touchscreen display, SD card slot, and other features perfect for this project. We will use the ST-Link virtual COM port to read debug messages during development. For more details on Qt for MCUs, check out the official documentation. I'll link it in the description to help you explore further. Our DrinksBar GUI uses many images. While this project is relatively small, imagine an app with multiple pages, large images, or even videos. To handle this, we use the SD card to store image data instead of the board's limited memory. This discovery board comes with a micro SD card slot, so it's easy to jump directly into the project without any additional hardware. Qt for MCUs provides an example for loading images from an SD card into QML views. I adapted this example to build a system that dynamically loads images from the SD card to QML view. I'll walk you through how it's implemented in this tutorial. In this video, I won't cover how to develop the UI with QML. If you're new to QML, watch my previous video where I explain UI development in detail, link in the description. If you saw the desktop DrinksBar from my last video, today we're building the same application for the STM32F769 discovery board touchscreen. The goal is to learn Qt for MCU with STM32. You can clone the DrinksBar project from my GitHub repository, link in the description, or start a new Qt for MCUs project from scratch. In either case, select the STM32F769I Discovery Bare Metal Build Kit. I didn't use FreeRTOS for this project to keep it lightweight. Also, configure the build directory. I created a build folder inside the project directory to keep build files organized and easy to locate. Let's jump into the project files and explore how it all comes together. Let's start by exploring the CMakeLists.txt file. If you created an empty project, you might notice at this line with generate entry point CMake macro. This automatically creates a main.cpp file for each build. However, we often need to initialize board hardware, and main.cpp is the place for that. In this line I have set a custom main.cpp file. This bare metal folder coming from the CMake macro. If we look at the build configuration kit, we can find those CMake macros are defined here. If we use RTOS, it will show the RTOS name. In here main.cpp file. It's similar to the auto-generated version found in the build directory. If I show you the auto-generated one from other project, what I did was copy the essential code from the auto-generated main.cpp, excluding unwanted lines, and paste it into our custom main.cpp. Additionally, here I have added a hardware initialization function. I will show you what it does later. To load files from the SD card, we need to use the FatFs library. In the CMakeLists.txt, we include the FatFs source files. Let me show you where to find them. In the Qt installation directory, navigate to Tools. Qt for MCUs. STM. You'll find the STM32 firmware folders here. Currently we are using F7. Inside, go to Middleware and then Third-Party folder. Here we can find the FatFs files. Also, you can find those third-party libraries in the STM32Cube repository directory. Copy the FatFs driver files to the third-party FatFs directory in our project. You'll also need to update the ffconfig-template.h file and rename it to ffconf. I'll explain the necessary changes for config file later in the video. Next, we need board_config.cpp and FatFs filesystem.h to configure the hardware for FatFs. These files are inspired by a Qt for MCUs example, and I'll dive into their implementation in a later. To parse the JSON file for drink data, we use JSON32F769I. In our desktop DrinksBar project from the last video, we used Qt's QJSON libraries. However, Qt for MCUs, or QUL, is ultra lightweight and doesn't include QJSON, so we use JSON instead. It's a lightweight JSON parser in C, perfect for resource-constrained embedded projects. Here is the JSON file we load the data of the drinks. And this file is also saved on the SD card and read from the SD card. Later I will show how to do that. Next is the systeminterface.cpp file, where we implement the core system control functions for DrinksBar. I'll dive into those functions in detail later. We also need to include several STM32F7 source files into the project. Let me show you where this CMake macro and these files comes from. In the build configuration kit, we can find this macro, and it is set to the STM32 firmware folder. From there, we can include the necessary files. The first three files support the FatFs file system. These contain APIs that are FatFs implementation of the STM32F7 MCU. The last two files handle the RTC implementation. Here in the screen I will show the RTC date and clock. Another key step is setting up the FatFs directory as an include directory, to use its header files. We also link to platform BSP config, which includes all necessary HAL and BSP files from the STM32F7 firmware folder. This ensures our project has access to the board's hardware drivers. Let's open the DrinksBar.qml project file. I've commented out several auto-generated sections, as they are not needed for this project. In the image files section, I've specified the directory for images loaded from the SD card. You might wonder, if we're loading images from the SD card, why include them here? In MCUs, we can't directly use file types like PNG or JPG. Instead, in the STM32Cube IDE projects and LVGL projects, we use images as raw data in a hexadecimal array format. Qt for MCUs provides tools to convert images into an optimized format for rendering on the target device. Here, I've set the pixel format and cache policy. This ensures images are efficiently rendered and loaded only when needed. For more details on these settings, check the Qt for MCUs documentation. I will leave link in the description. Another critical setting is the max resource cache size. This value must be larger than the size of the largest resource with the on-demand cache policy. Ideally, it should accommodate all on-demand images visible at the same time to avoid repeated decompression or copying to RAM during frame updates. In DrinksBar, I dynamically load pages, so images are only loaded into RAM when visible on the display. For example, one page shows up to 8 images at once, which is the maximum number of visible images at any time. To set the max resource cache size, I calculated the memory needed for these images. Here in the Qt documentation, they mention how to calculate this. Read that for more information. After adding these image converter policies, build the project. Let's check the build directory. Navigate to CMake files. DrinksBar.dir. Resources. Assets. Images. You'll see the converted image files here. If you try to open one, it won't work because the format isn't a standard PNG or JPG, it's a different format optimized for Qt for MCUs. Interestingly, the converted files are often larger than the original images due to this optimized format. You know that the raw data of the image is much larger than this. Qt has done a good job converting it to make it simpler. To use these images, copy them to the root directory of your SD card. You don't need to copy any text files in the build directory, they only contain conversion metadata. Before copying, ensure the SD card is formatted in the FAT32 file system, as required by the FatFs library. I've also included two images, jpn.png and uk.png, as regular assets embedded in the application binary, not loaded from the SD card. These are used for static UI elements, in language selection icons. Next, let's look at the font files section. For DrinksBar, I've included fonts to support Japanese translations. These fonts ensure proper rendering of Japanese text in the UI. In the translation files section, I've defined the Japanese translations for the app. This file, drinksbar_ja_jp.ts, contains Japanese translation of the text we used in the app. The interface files section is where we set our interfaces used in the application. I'll explain these files in detail later. In the MCU QUL modules section, we define the Qt for MCUs modules used in the project. Here in the QML files, I have set the UI directory. All of my UI files are in this folder, so we don't need to give each UI file name one by one. Same as the image files. Let's look at the QML files in the DrinksBar project. The DrinksBar.qml file serves as the main QML file, loaded when the application starts. Here, a loader component dynamically loads QML pages based on the system interface current page property. In SystemInterface.h, here we define the bindable properties of the system. The current page property is defined as a QUL property with type std string. This QUL property can be directly bound to the QML view. When its value changes, the UI updates automatically. Other properties in system interface, like selected drink name and sugar level, work the same way. Now, let's open QUL select screen.qml, the initial page loaded by the loader. This screen displays the drink category selection. Here, two images are loaded from the SD card, with their source properties set to paths like file:/image name. Let's break down how this works. In FatFs filesystem.h, I created a FatFs filesystem class that inherits from QUL, platform interface, filesystem. This class overrides the open method to use FatFs as file opening functions, returning a QUL file object. The FatFs file class, also in this file, inherits from QUL platform interface file and implements methods like read and close for SD card access. To use this file system, we register it in the board_config.cpp files configureboard function. This function initializes the FatFs file driver, mounts the SD card, and adds the FatFs file system to the Qt for MCUs application. The configureboard function is called from main.cpp during application startup, enabling SD card access for dynamic image loading. These setups you can check with a Qt example for file loading. Let's talk about an important file, ffconfig.h. This file configures the FatFs library for SD card access. For this project, we didn't need to change most settings, so the default values work fine. However, you may need to adjust them based on your project's requirements. Let me show you one key setting, _USE_LFN. By default, this is set to 0, which disables long file name support. In here, I changed it to 2 to enable long file names with a dynamic working buffer on the stack. If your file names are short, like the 3-character names used in this project, such as img.png, the default setting is fine. But for files with longer names, you need to enable long file name support by changing this value. This ensures FatFs can read those files from the SD card. Now that we've covered image loading from the SD card, let's see what happens when we select a hot or cold drink. If we select the hot drinks, the current page property changes to hot drinks select screen.qml. Let's open this file. At the top, you'll notice the hot drink model. What is this model? In the interface folder, we have drinksmodel.h. This file first defines a drink item structure. That drink structure that mirrors the JSON drink model. The hot drink model class inherits from QUL list model, using drink item as its data type. In the hot drink model constructor, we call the load JSON data method to read the JSON file from the SD card. Using the FatFs file system, we load the JSON file as a string. Here we pass the JSON file name to load from the SD card. To achieve this, you need to copy this JSON file to the SD card root directory along with the image files. The load text file method, we load the JSON file as a string, similar to how we handle images but without opening it as a FatFs file. Then return the string data. Here, get those string values. Then, if the data is loaded, print the message on the console. After that, string data parses the JSON string using the JSMN parser to extract drink details, like names and image paths. So that's why we include the jsnm.h file. Then set that JSON data to the drink item and append it to the hot drink models list, making them accessible in QML. This data variable represents the hot drink model dynamic list. What we pass to the load JSON data method. Don't forget to include drinksmodel.h in the interface files section of QML project file. Back in hot drink select screen.qml, I've imported Qt quick layouts and used a grid layout to display drink items. A repeater sets its model to hot drink model. That is what we define in the drink model and store the loaded JSON data. The delegate is a drink item delegate component which defines how each drink is displayed. In the drink item delegate, the image component source is set to model.image, a property from the hot drink model's drink item. Dynamically loads the drink's image from the SD card. When a drink is selected in the grid layout, we update the selected drink name property in system interface. These properties initially set to empty strings. Then, the app navigates to the size select screen. Here, we use the selected drink name to display drink details. When a size is selected, we update the size property in system interface. For hot drinks, we navigate to a sugar level select screen for additional customization. For cold drinks, we go directly to the confirmation screen. I won't dive into the details of creating the QML UI, as I covered that in my previous video, link in the description. Check it out if you need a refresher on QML design. Another key feature is the busy indicator on the preparing page.qml. In the desktop DrinksBar app, we used Qt's built-in busy indicator. However, Qt for MCUs, or QUL, is lightweight and doesn't include this component. Instead, I created a custom busy indicator using a shape with an arc, rotated with a number animation from 0 to 360 degrees in an infinite loop. Component on completed, call the start preparing method in system interface. This start preparing method triggers a QUL timer. This would send a command to prepare the drink, but since I don't have hardware, it simulates preparation with the timer. In QUL, the timer setup different from normal Qt timer. Here in the constructor, set timer single shot to true. And just set the timer interval to 3 seconds. This done timeout is a struct that holds a pointer to the system interface instance. In its operator, we call the done drink order signal a QUL signal. When the timer times out, it triggers done timeout, which emits done drink order to signal that the drink preparation is complete. Let's examine the preparing drink screen.qml file. I've connected the on done drink order signal, which triggers after the timer times out. When the timer's timeout function is triggered, it sets the current page property to enjoy message screen.qml. In enjoy message screen, I set a 2-second timer that starts when the page is completed. When the timer triggers, it clears the selected drink properties and navigates back to hot QUL select screen. In DrinksBar.qml, I've added a custom topbar component. In topbar.qml, I set a timer with a 30-second interval to update the real-time clock. The timer's repeat property is set to true, triggering every 30 seconds. The datetime provider is another interface in DrinksBar. It provides functions to interact with the MCU's RTC clock for real-time clock updates. In the refresh datetime method of datetime provider, I call the getRTCTime and getRTCDate functions. Let's check these functions in board_config.cpp, where I've implemented them. They use the HAL_RTC_getTime and HAL_RTC_getDate functions from the STM32F769I drivers. In board_config.cpp, during board configuration, I initialize the RTC. This is similar to generated from the STM32F769 when we use the RTC clock. However, initializing the RTC isn't enough, we also need to configure the system clock. How do we know the initial configurations used by Qt for MCUs? In the build configuration, you can find the board platform directory. Open this directory in a file explorer, navigate to the Discovery Board's common folder, and check the platform_clock.cpp file. Here, you'll see the system clock config method, marked as a weak attribute, allowing us to override it. I copied this function into our project, so the system clock is now configured from our own code. I configured the oscillator type to use both HSE and LSE, with the LSE state set to on, and the PLLR set to 2. The how_RTC_MSB_init function is also implemented here. This function initializes the hardware-specific settings for the RTC, ensuring proper operation. Also, I've defined the setDateTime method, which resets the RTC time and date. This method is called from the DateTime provider interface. The refreshDateTime function runs every 30 seconds to update the displayed time. In DrinksBar.qml, at the bottom, I've added a custom settings dialog component. The settings dialog's opacity is tied to a configuration enable fading animation variable. Let's check the configuration.qml file in the configuration folder. Within a Qt object, I've defined a read-only Boolean property called enable fading animation, set to true. This shows how to define configurations for Qt for MCUs projects. In the same configuration folder, I've created a DrinksBar configuration.qml project file, which specifies the configuration.qml file and the MCU.model UI for accessing configuration properties. In the main DrinksBar.qml project file, I've added this configuration project to the module files section. This setup allows us to access initial application configurations easily. Here opacity becomes 0, because we set the enable fading animation value to true. Let's explore the settings dialog custom item. This is the pop-up window to set the time of the system. When opening the dialog, a sequential animation sets its opacity from 0 to 1. To close the dialog, another animation sets the opacity from 1 to 0. For other setup details, you can review the code. I won't cover everything here. When you click the Set button, the setDateTime method updates the RTC date and time to a new value. And then close the dialog. Next, let's look at the translation. In QUL select screen.qml, I've added England and Japan flag images for language selection. Clicking the Japan flag sets the system UI language to Japanese, while clicking the England flag reverts it to the default language. This demonstrates how to easily toggle languages in Qt for MCUs. Let's wrap up this DrinksBar tutorial. We built an embedded drink ordering system using Qt for MCUs on the STM32F769I discovery board. Key features include dynamic image and JSON loading from the SD card, a real-time clock, and multilingual support with Japanese translations. Check the code on GitHub, link in the description, and explore the Qt for MCUs documentation for more. Thanks for watching. Like, subscribe, and comment. See you next time.